Hello, everybody. It is the 29th of April, and we are on lecture number 5, or we're beyond halfway point now. Pretty much everybody did the mid-block quiz, all except for one, and that's going to be probably done today. And everybody is doing reasonably well. We have gotten past that midpoint, and we will now move boldly into the second half of the weather portion of AER 110DE. And with that, we will take a look at the cloud cover, which is pretty sparse across the entire region. You can see a little bit of cloud cover here in the foothills of the Sierra, just to the north and east of Bakersfield. Also down to the south in the San Pedro area, there is a little bit of a low cloudiness. Was some low cloudiness in the San Diego vicinity earlier, and it's just completely clean over in Arizona. We can take a look at a couple of observations here. Let's see. Well, here's the synoptic weather map, and it shows that Bakersfield is 71 degrees now with northwesterly winds. At Camarillo, currently 71, Oxnard 64, all with good conditions. Looks like we don't really have any problems anywhere. A little bit of haze here in the Oceanside area, just a little bit. San Diego looks to be good right now with partly cloudy skies, a few clouds at 1500. And we'll take a look at what took place earlier today. We'll go and check out, well, not Omaha. Omaha had just tremendous tornadic action on Friday. That was a bad day there. But we'll take a look at this. In fact, yeah, there was a lot of severe weather over the weekend. On Saturday evening, 4 people were killed in southern Oklahoma due to tornadoes. It's that time of year, though. Of course, we do get tornadoes in the middle of the country, especially in April and going into May and June, too, I should add. That's the severe storm season. All right, here is the weather observations from Bakersfield. Looks like we had a low temperature this morning of 10.0, which is exactly 50 degrees Fahrenheit. Winds now northwest at 11 knots and clear skies, and all's right with the world. Let's see here. It wasn't much easterly wind this morning. Sometimes we get easterly winds, like a 120 wind in the middle of the night and very early in the morning. Not today. And the forecast is for a little bit of gustiness going into the afternoon and clear skies. SKC clear. It's clear in the Oxnard area. Winds light out of the west-southwest, 9 knots. Looks like good visibility, and it looks like it's been pretty much clear the whole time. There was a little bit of cloudiness right there, a few at 700, but not more than half the sky. In fact, not more than 1 or 2/8 of the sky. So pretty nice weather. And it looks like it's going to continue. Clear skies for the rest of the next 24 hours in Oxnard. San Diego. Well, we did have some ceilings here at 1500 broken. That was as recently as 17Z. A little lower than that. In fact, we were down to IFR right here. 900 broken, with 800 broken right before that. So we did have some low cloudiness for a little while, but as you saw, it burned off. So the forecast says, here's the San Diego forecast: light winds, clear skies, temporarily between 6 and 9Z tomorrow morning, late tonight, 900 broken. And then they're going to just go consistently 900 broken from 9Z. Comes up to 1300 broken at 13Z, going from IFR to marginal VFR, and then we're VFR again at 17Z tomorrow. Phoenix, of course, there's not a cloud in the sky. Clear skies, they're already up to 31 degrees Celsius, which is 87 degrees Fahrenheit, and the skies are forecast to remain clear. So the weather's fine here. There's no problems whatsoever anywhere across the region. And so the question is, what's it going to look like into the future? And there's a very interesting situation developing. Let me tell you about that. So let's go to we'll go to kind of the big picture here. We'll go to this. Here's continental. We're going to take a look at the 500 millibar pattern. And so this is the GFS, the Global Forecast System, and you'll notice that as we go into the future here, this is the 12Z run. So as we go into the future, Let's go back into the future. Oh, I know. Let's do this. Stand by. Gotta change something here. Go to that, and then we'll go to this. And now it will work. Okay, so here we are down here over California, and all is well. We have a little bit of a trough, which is an elongated area of low pressure across the west. You can see it right there. And then as we go, and time is in the upper right, left-hand corner there. There is time. So we're down here once again, trough of low pressure. But then we have this interesting little low over here, which is just off of the Aleutians. And this is for Thursday. So let me go backwards just a little bit so you can see where that low is right now. In fact, it's someplace in near Petropavlovsk. It is in far eastern Siberia. That's where the low is right now. So the model is taking that energy from that low, and here's Thursday. And then right about here, it's going to make a little bit of a right turn and dig down into California, right like that. Okay, that is where the low is going to be according to the model for Saturday night going into early Sunday. This is 12Z Sunday morning. We have a big low right here. And this is the same low again, which is currently over eastern Siberia. So this model, this is the American model, is saying that there's going to be not only cooler weather, but a chance for rain. It actually brings a chance for rain. Well, that is, let me see when that is here. Once again, that is the right about here, there, we'll go there. Okay. So that's the 138-hour forecast. So let's go ahead and go to the 138-hour forecast here. There it is, big low. All right, but if we look at other models, let's go ahead and look at the Canadian model. Same time, it has the low pressure system not over central California, but way up here over Oregon and far northern California. That's the Canadian model. Now we'll take a look at another one. Let's look at the German model. The German model also has it even farther to the north, centered over the Willamette Valley, nowhere near central California. Okay, let's look at, how about the UK Met? Okay, so UK Met doesn't have that projection, but you can see that the low is farther to the north. That's really kind of a big deal. It's a huge deal, in fact. Let's go back to this. We're going to look at the AI version of the European model. It has the low way up here. Again, but let's go ahead and go back to the continental. We'll take a look at this. And there it is. Okay, but if we look at the American model again, it has the low much farther south and having a significant impact on our weather here in California. So now we're going to go ahead and take that and move it forward. There it is again. It kind of flares right about there and then moves on through. And then after that, it looks like it's pretty much high pressure. So the question is, will it or won't it be a big deal? Will we have low pressure over the weekend or not? All right, let's take a look then at the MOS data. This is the model output statistics, which we will talk about today, by the way. So here is Bakersfield. I'm just taking Bakersfield. We could take some other spots. And this is the GFS, the Global Forecast System, the American model X, which means extended. So we're going to go Tuesday, Wednesday, Thursday, Friday. Here we're going to Sunday. And here is the probability of precipitation. You'll notice it goes all the way up to 61%. The 24-hour pop is 61% on Sunday. And this Q right here, that is the quantitative precipitation category. And the 3 that you see right there means more than half an inch. So that is, you'd have to say, significant precipitation coming late Saturday going into Sunday. But if we were to look at the national blend of models, which takes about 35 different models and sort of blends them together to come up with an integrated output, here's what we have. Okay, so this is sort of the same, not exactly, but sort of. So here are days up here, Friday, Saturday, Sunday, Monday. We're talking about the Sunday, Monday time frame. Here's the probability of precipitation, and it goes all the way up to 6%. That's it, 6%. That's not a lot. And as far as sky coverage right here in percentage, it goes all the way up to 41%. That's not even a ceiling. So, and as far as the quantitative precipitation, 0. So there is a major discrepancy between the American model, which says here comes a low pressure system that's going to give us rain, and basically all other models. So are all the other models wrong and just the American model right? Or is the American model onto something here and nobody else seems to know about it? Once again, 61% probability. Let us then look at, we'll take a look at this and we'll come right down to the regional here and see what it says. As far, and this is the GFS, that is the American model. And of course, models are so important today because, well, as you're going to find out, they are pretty much the default. The National Weather Service doesn't actually forecast the weather anymore. People don't do, well, what I do is called artisan forecasting. It's sort of like an artisan chef. He takes all of the ingredients and he just makes something really special, kind of from his own mind. He kind of, and it's usually really, really good. It's high quality. If you go to McDonald's, you don't have artisan chefs there. You just have industrial food. Well, we're to the point now where all of the forecasts are basically industrial forecasts. They are just spit out by what the computer models say. Now, that's good and bad because the computer models are really good now compared to like 20, 30, 40 years ago, but they're not always right. So let's see what this says. We're going to go ahead and take a look. We're going to go into the future here and see what the global forecast system says. And it brings right there. You can see the rain coming. There it is. This is for Saturday morning, just coming into the Bay Area. We go into Saturday evening. It's approaching San Luis Obispo. And then there it is. This is for late Saturday night, early Sunday. Not only do we have rain, we have snow in the Sierra, and we have snow. It looks like we have snow in the Tehachapi Mountains. And that's for Sunday morning. And then it continues into Sunday afternoon with lingering showers. You can kind of see them right down here. Lingering showers as the weather system pushes on through. And finally, by Monday, it's gone. Okay, so this is the lone wolf, which is saying that we're going to have some big deal here. You can see the thickness numbers right here, the 534, the 540, which I haven't really gotten into too much, but we will in the 300 course. This basically is temperature. So the lower those numbers, the colder the entire atmosphere is. So if we look at the quantitative precipitation forecast, how much rain is going to fall? Let's see what it says. All right. Whoa, 0.72. All right, now I got to get a little bit closer. So let's get right down to the local level here and see what it says as far as QPF. All right. So here it is. So this has just a little bit over here, 500ths of an inch up around Lost Hills. But in the Bakersfield area, probably a half inch of rain. In the mountains, 8200ths. Over here, we have 7100ths. LA gets 0.2 of an inch, and even 1/10 of an inch in the San Diego area. Now I have to look at winter weather and see if it's going to give snow to the passes, which is going to be a real outlier if it does. And the answer is it does, right there. Okay, so this is giving maybe 2 inches of snow to the Tehachapi area. Maybe an inch. Up here in the High Sierra, there's 36 inches. That's 3 feet of new snow. Okay, so that is what the GFS model says. Now, let's look at something else. Let's go to the Canadian model. How much snow does the Canadian model give us? We'll go to regional and look and see what it says. So here's the Canadian model, the same time frame, and it gives 0, absolutely nothing. Some snow way up in the High Sierra, High Central Sierra. We'll take a look at the ICON model. This is a German model. What does it say? Nothing, absolutely nothing. And then I could do that for all the other models and it would be the same. So how do you know? How do you know? We'll take a look here at just regular precipitation, QPF, and see what the ICON model says. It brings a little bit of rain about as far south as north of Fresno, certainly about the Madera area, maybe down to the Salinas and Monterey area, and up here right around Mammoth, perhaps a little bit of something. That's the ICON model. But again, if we go to the American model, it goes bonkers. So there is a major discrepancy, as I've said. We will see what actually transpires with that. Is one of the interesting things. This is one of the reasons why we have people that look at all of the data to see what it says. If we were to look at that wave right now, we'll have to go all the way over here to this part of the world, right up here. So it looks like that wave is somewhere up here, right around Kamchatka right now. And so the model has to take that, and then it has to balance it out with what's happening in the rest of the world. That's why it becomes such a difficult proposition. Let's go to this here. Okay, so we're going to go to global. We'll go to West and put it in motion if we could here. Let's go here. So there we are. Interesting situation. This weather system way up here over the Sea of Okhotsk is projected to give us rain in a little less than a week. And so how good are the models? Well, the models do not all say the same thing. Very interesting scenario there. By the way, while we're looking at a few other things, let's check out what's happening in the Gulf of Mexico, this area here. There have been some big thunderstorms across the northwestern Gulf of Mexico, and there were huge tornadic storms the other day in Oklahoma. In fact, I can take a quick look at that. Let's go to the SPC site, and we'll look at storm reports, which you can always do. We'll go back a couple of days, and on what was interesting that was on Friday, there were 92 reports of tornadoes and only 37 wind reports and 61 hail reports. It is very unusual to see more tornado reports than wind and hail, because tornadoes are sort of specialized. See here, and here's the unfiltered reports, 121 tornado reports. You filter them, there's a little bit less, but there was a lot of damage there. But the next day, on the 27th, which was Saturday, then we had 42, and this is more like it, 124 hail reports, 71 wind reports, and only 42 tornado reports. But of those 42, there were a number of fatalities. Here's one in Hughes County, Oklahoma, one fatality, a large TDS, which is a tornadic debris signature, which is in the upper atmosphere, meaning that the radar can see things that should not be 30,000 feet in the sky, like billboards and tennis shoes and things like that. It should be, precipitation, should be hydrometeors and stuff, not. So when that happens, it can only come from one place. A tornado sucked the stuff up. Here in Sulphur, Oklahoma, there were a total of 4 fatalities. So a lot of bad weather there. Anyway, we're looking at our current situation, and let's go back to that. Here it is. You can see these big thunderstorms that are developing down here. And if we were to look at radar, you can see this line is just sort of pushing down into the Gulf of Mexico right there. Let's look at it on, let's look at it here. We'll come over here and we'll look at the weather off the coast of Texas here. You can see, some very gusty winds, and some of these are all oil rigs down here where there have to be weather observations taken so that the helicopters can land there. Yeah, helicopters take you to all these locations if you're going to fly there. Anyway, so yeah. So the dew points are in the mid 70s out ahead of this system. And if looking up over here, by the way, you can see that the dew points do begin to drop off. Here we have dew points in the mid 70s. Of course, the higher the dew point, the more molecules of water vapor are mixed into the atmosphere, the lighter the atmosphere is. And as we go back from Austin with a dew point of 71 to Brady with a dew point of 48 to dew points in the 20s over here at Fort Stockton. Very, very dry. That's where we set up dry lines, and these thunderstorms like to develop along dry lines. But taking a quick look here at the dual pole radar from that part of the world, let's go to Galveston and we'll put it in motion. And what do we have? We have some big thunderstorms over here, which are pushing, and it looks like another one's developing onshore over here. What are the tops of these things? Let's look at the tops. So the tops are getting up into the, like I saw one brown there, right about there. And that would be 50 to 54,000 feet. So a lot of bad weather in that part of the world. All right, so that's all taking place. Let's see if anything else is going on just very briefly. Then we'll get into today's topic. Of course, with us, nothing is going on. It's just fine here. And there's a big low pressure system up over the northern Mississippi Valley. And you can see it's still solidly iced over here across northwestern Ontario. But it does look like Hudson Bay is beginning to open up here a little bit. Still some pack ice, but it's looking a little bit less iced in, especially here on the eastern portion of Hudson Bay. You can actually see some of the ice flows moving there if you look at the loop. And over here, we still have solid ice in Lake Manitoba. And just to the south of there, what do we have? Let's see here. Big low pressure system. There it is. And we'll put it into a mid-level water vapor imagery. And you can see where the low is there. A little bit of dry air kind of coming in here. And at the Mosaic radar shows, let's look at the Mosaic radar. Oh, it doesn't show it. Interesting. Okay. I guess, why didn't it show it? All right, now I'm curious. Let's come over here, do this. Now we're going to look at the Mosaic radar or else. Okay, it doesn't show a whole lot of precipitation, just mainly very cool air. And these are some cumulus clouds coming in behind that weather system. Where it is probably very cool and breezy. Let's see up here in the northern Mississippi Valley, after the front's gone by, temperatures are in the 40s, a little bit of light rain. We got 2,000 broken, 2,600 overcast in Huron, and gusty winds. All right, so that's what's going on there. We already looked at the models. The models show great weather for us, but the big question is, will it or won't it be wet this weekend? And right now we cannot be sure one way or the other. All right, let's see here. Okay, we do have Travis, you're with us right now. Thank you so much for coming on board. Good to have you. Let's take a look. Let's take a look here at the test that we took. So here is the mid-block test from this past couple of days. One person actually aced it, so congratulations to that individual. Many people did not ace it, but did relatively well. So here we go. The greenhouse effect warms the atmosphere primarily through blank radiation from the blank. Okay, that would be long wave radiation from the Earth. That's the greenhouse effect. The greenhouse effect does not happen from the sun. It happens from the warmed Earth, which re-radiates into outer space, long wave energy at just the right wavelength that it resonates with greenhouse gases. Of the following atmospheric gases, which is the most impactful with the greenhouse effect? So we have all of these. Let's see, we have oxygen, we have sulfuric acid, carbon dioxide, and water. And of course, you might think carbon dioxide is the worst thing in the world. We're all going to die because of carbon dioxide, carbon this, carbon that. But that is not the correct answer. The correct answer is water vapor, which is much more impactful as a greenhouse gas than anything else, including carbon dioxide. All right, wind is fundamentally caused by what? Well, fundamental, we're going to be the fundamental here. Differential heating of the Earth. You know, a lot of you said high and low pressure systems, and I understand that. But what causes high and low pressure systems? It's differential heating of the Earth. Water vapor pressure will be greatest with, let's see what we have here, higher temperatures. That is the answer. Higher temperatures will allow for a greater water vapor pressure. Clouds will most likely form on the blank slope and less likely form on the blank slope of a mountain. Well, they'll most likely form on the windward side, and they'll less likely form on the leeward side, which is the other side. One is upslope, the other is downslope. So they're going to form on the upslope portion. Showers are a blank of precipitation. Many of you said intensity. The answer is not intensity. Intensity would be like light, moderate, and heavy. It is not a type of precipitation necessarily. Rain and snow and drizzle, those are types, but it is a character of precipitation, a character. The other two characters are continuous and intermittent. Those are characters of precipitation. Very much like gusts are a character of wind. All right, a stable air mass features what? So we're going to be stable now. Well, it looks to me like it'll be warm air above cool air. Warm air wants to rise, so if it's already up there, great. Cool air wants to sink, and if it's already on the ground, everybody's happy. So that would be stable. The opposite of that, let's see, cold air above hot air, that would be unstable. Conditionally, a conditionally unstable lapse rate is one that, let's see, conditionally unstable. That would be between the dry and the moist adiabats. So the dry adiabat is cooling off at about 3 degrees per 1,000 feet. The moist cooling off at about 2 degrees per 1,000 feet. So somewhere between those two is where you would find conditionally unstable. It means that it's not necessarily unstable. It would be if the lapse rate was cooler than the dry lapse rate. But if it's in between the dry and the moist, then it depends. You know, if there's a cold front coming, if there's a mountain range or something like that, or some boundaries coming along, then it might become unstable. The level of free convection is a point on a skew T where, okay, let's see. Looks like the lifted parcel becomes warmer than the environment. So the lifted parcel is being lifted by one method or another. And by the time it gets to this point, the level of free convection, now it's warmer than the environment. If it's warmer than the environment, that means it's less dense. It wants to rise, and it will. So the less dense air then just rise all by itself. It's free to rise. That's the LFC, the level of free convection. The area to the right of the temperature curve, okay, here's the temperature curve to the right, and to the left of the rising parcel on the skew T is called, well, it is called CAPE. Now, which CAPE? Convective available potential energy is what it's called. And the bigger that area to the right of the temperature curve and left of the rising parcel, the bigger that area, the greater the CAPE, the more unstable the atmosphere is and more likely to become a convective precipitation zone. What are the effects of atmospheric instability? Okay, let's see what we have here. Okay, looks like it will be this one here: increasing turbulence, increasing convection, and decreasing predictability. That is how we know. So decreasing predictability is one way that you know that you have an unstable air mass. Almost to the end here. Synoptic weather means, what does it mean? Well, it means weather features. Anything that you can plot on a map. A high, a low, a front, those are all weather features, and those are also known as synoptic weather. Okay, and it doesn't mean sinful weather. All right, let's see here. Developing front, well, a developing front is called frontogenesis. It's the beginning. Frontalysis is the end of a front. What is a lithometeor? Well, a lithometeor is simply a dry atmospheric phenomenon. There we go, right there. A dry atmospheric phenomenon. Haze, dust, um, blowing dust, smoke, things like that. Those are all lithometeors, coming from the Greek word litho, which means earth. And last but not least, liquid rain that freezes upon contact with the ground is called, well, freezing rain. That's the only type of weather well, no, I was going to say the only type of weather that has a verb in it, but I guess blowing dust has a verb in it. Yeah, blowing. All right, so freezing rain. That is the rain is going from liquid to ice right before your very eyes. Okay, so that's that. Hey, Barbara's with us right now. Cool. Hi, Barbara. How are you today?
I'm pretty good.
Oh, good. Hey, we haven't checked your weather. We better do that right. Let's see. I'll bet it's good. Let's see what we have down here. Okay, so here we go. Clear, 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 clear. Let's see. That's clear, but I don't care about Van Nuys. I want to know what the weather's like where Barbara is. And that's Fillmore. So we're going to do this, and we're going to do dew point, and see what we got here. Fillmore, 74 degrees. That's perfect. Very nice. And you had a low of 47 this morning. Kind of chilly, but a nice afternoon. And as I can recall, let's go ahead and take a look at your satellite, not South Dakota. It looks pretty good. Was there any low clouds this morning? I don't know. I don't think so. Have you gone flying today?
No, I haven't.
Are you going to go flying today?
Not today.
That's too bad. It's a great day to go flying.
It was a beautiful day yesterday, so I made up for it for today.
Ah, I see. Okay. Very, very, very good. All right. So we are done with taking a look at the weather here. It's all pretty good. We have some gravity waves right there across the Ely area and parts of Utah. By the way, we watched Butch Cassidy and the Sundance Kid last night, a classic old Western movie from the late 60s with Paul Newman and Robert Redford. And so I want to know, where was all that filmed? And it turned out it was Zion National Park.
Mm-hmm.
That's where it was filmed. And the train scenes were over here in the Durango, Silverton area. So that was kind of cool. So I learned something. And also that, let's see, Catherine Ross has been married 5 times and she's still alive. And so that's what I know about that. All right, so let's go ahead and go right into what we're talking about today, which will be an exciting class. Talking about, and we talked about it earlier, computer models. As you know, we have a big controversy. And Barbara, if you weren't with us before, the controversy is, will it rain this weekend? Well, the American model says yes. And literally every other model in the world says no. So who is right? Well, and it's all about weather models. So we'll see. Actually, what you have to do sometimes is take the track record into account. You know, how good have they been, and how good have the others been? So introduction to weather models today, and so weather over the ages. You know, weather really is important. How important is weather? Not just to aviation, but to everything. I mean, there was this big parade in San Antonio over the weekend, the Battle of Flowers parade. And if it had rained, well, there wouldn't have been the big parade, but it didn't rain. The art of weather. Okay, now we're going to talk about 2 different ways of kind of looking at this. And you could look at anything like this. You could look at the art of driving your car. You know, there might be an art to that. And then, of course, there's a science too. But anyway, the art of weather. Here's a neat picture by a guy named, or maybe a gal, let's see, K.B. Hudson, looks like. It's a beautiful scene there. Looks like a sunset with a nice rolling hills. Looks like a little silo there. Well, it's important to know about the weather because we've all got to eat. And in order to eat, we have to have rain because plants really do need water. It's just like people need water. We're 70% water. Our bodies are just like the world. And so water is the constant among all living things. Got to have water. Weather has always been a critical element in human survival because of crops. In areas where it never rains, there's not a whole lot of life. There is some. There are some places like the Atacama Desert in northern Chile, the Kalahari Desert in southwestern Africa, where it almost never rains. But even in places like that, there is a morning mist that sometimes develops due to high dew points. It's a desert, but a little bit of mist in the morning can be enough to keep some plants going. So the art of weather has always been important. And back to the art of weather here. So farmers for the longest time had to get some idea of what the weather would be like. And we're talking, the 1800s and prior to that. Actually, way prior to that, people just basically picked berries and fruit from trees and stuff like that. And but then agriculture was a new paradigm. And once we had, a kind of a scientific way of planting crops, so that there was some certainty to the crops, and we would do them routinely, and we would rotate crops and stuff like that. That was a whole thing, agriculture. It was a paradigm shift. It's a change from the hunters and gatherers. Then after that, we came to the Industrial Revolution, and that was a paradigm change. Now we can make things in factories on assembly lines, and it changed the life of humanity. Then we have the information explosion of the internet, and that too is the next type of paradigm change that completely changes the way everybody lives their lives. But going way back to the beginning, agriculture was one of those first things. So we have that, and the farmer, here's Farmer John right over here, and he looked at things like woolly worms and horse manes, and just the way the animals would do whatever they were doing, to see whether or not there was some indication from nature that it was going to be a good year, a bad year, whatever, hot and a drought, or lots of rain, or maybe even some bad weather. Even Punxsutawney Phil, you know about him. That was part of the art of weather. Punxsutawney Phil is this groundhog who lives in the ground in western Pennsylvania and Punxsutawney. And back at times when Farmer John was there, and even before that, people would get to the midpoint of winter, which just happens to be February 2nd. That is halfway between the winter solstice and the vernal equinox, first day of spring. And so they would want to know, well, we made it through the first half of winter. Will we make it through the second half? And so what they would do is they would say, I know, let's consult the groundhog. He lives in the ground right where all those crops are. He'll be able to tell us whether or not it's going to be a really cold second half of winter or not. And so so on this midpoint of winter, and that's why it's important, it's a midpoint. It's like May Day, which is coming up day after tomorrow. That's the midpoint of spring, halfway between the vernal equinox and the summer solstice. We also have, we have that. We have the midpoint of autumn, which is All Saints Day, but the day before that is Halloween. So that's about the right time. There's really the 1st of November, but we all think of Halloween as All Hallows Eve. And then there's a thing called Lammas Day, which is the 1st of August, which is the midpoint of summer, which nobody knows about. But I did a whole big thing about Lammas Day a number of years ago, because it was based on Groundhog Day. So Groundhog Day, if the groundhog sees his shadow, he will then think that it is a groundhog eating monster, and he'll go back into the ground. And if he goes back into the ground, that's a bad sign. That means the crops are going to stay in the ground, But if he comes out because there is no shadow to scare him, then that's a good sign. That means that winter will last just a few more weeks, and then everything will be fine. That is the mythology of maybe the mythology. We say art here. We could say mythology. But anyway, that's just, you've seen these things before. Red sky in the morning, sailor take warning. Red sky at night, sailor's delight. There are all of these little things that people remember. That's the art of weather. But now we're talking about the science of weather. The science of weather is a lot more rigorous and exacting, uses numbers and things like that. So here we are all the way up to the very top. And so the science of anything is critical today. It's part of the new paradigm. It's sort of part of the Industrial Revolution, part two, where we build things that are very, very complicated using physics and mathematics. Physics and mathematics. That's what engineering is all about. Engineering the roadways, the bridges, understanding the stresses, how much weight a bridge can take. I mean, and also if it's going to expand and contract due to temperature changes, if it's going to be able to withstand an earthquake. All of these things are part of engineering, which is intimately married to the physics and mathematics of it all. Here's the Hoover Dam or the Boulder Dam. It is a huge work of engineering. It's holding back, millions and millions of tons, acre feet of water, Lake Mead. And at the same time, it's hydroelectric. So there's all sorts of science going into that. There's the Golden Gate Bridge. It too was a big deal back in the 1930s when it was built. Took a while. A big suspension bridge like that over a large area. There's a lot of calculations that engineers had to make before they could actually build this. You come up with the idea, then you put the idea into action, and you actually build the bridge. With these skyscrapers, man, that's a big deal. All of those have to be built with the understanding of stresses and temperature and how much wind it can take, and a lot of things to consider here just in San Francisco. There's a lot of engineering just in this picture right here. You can see some ships as well. Ships and these big metal things that can actually float. What? You might not, a couple of hundred years ago, you'd never even think of something like that. It has to be able to float like wood can float. But in fact, when you're talking about displacement, you can get this big metal thing that will float, which is counterintuitive to some people. Not only that, look at all the containers that are on there. How many, hundreds and thousands of tons of product are on there. And then, of course, we get to aircraft, which is just a modern miracle in itself. Not only do you have to put together this fuselage inside where people can live temporarily comfortably with air pressure and temperature similar to what they see on the ground, but you got to fly through a fairly hostile environment, 30, 35,000 feet. And then, of course, there's the whole power plant, the engines themselves, which is just another miracle. And then, of course, there's just so many things. Avionics, even the shape of everything is maximized through physics and mathematics. They can simply figure out what the optimum is for any parameter you're talking about. The wheels have to have a certain strength and ability, and they have to be placed at just the right spots. So there's an awful lot to it. And the mathematics we're talking about here is calculus, which is basically talking about the rate of change. It's all about the rate of change. That's what this is right here. You take the derivative of something, and that's basically the rate of change. But you can take the rate of change of the rate of change. You get a second and third and fourth derivative. You go the other direction with integration. So all of this was developed by two people, actually. This guy, Leibniz, and also at the same time, unaware of it, was Sir Isaac Newton. And they kind of figured this whole thing out simultaneously. Anyway, so all of that is part of the science of engineering, the science of weather, which is not really the art anymore like it used to be. So we have a scientific method, and this is somewhat new. There's really not an art method, or maybe there is an art method if you're painting something. Of course, art is more than just painting. Art can be music, it can be ideas, it can be sculptures, it can be anything artistic, but we're not talking about that. We're talking about science. So the scientific method really comes in just several different parts here. First, you see something and you say, I wonder about that. And then you ask a couple of questions and you observe. You take rigorous observations about whatever it is you don't know, but want to know more about. And you do research through extensive observation. You're researching the whole thing. You're going into great detail. And after you have this voluminous database, and you've got all of these things that you do know, then you develop a hypothesis. You want to know, why is it that it does that? And you say, here's an idea. Let's maybe it's this. Then you test the hypothesis with experimentation, and you see if it repeats, if it works every time. Then you analyze the data, your experimentation, sort of like you did with the extensive observations. You were doing research, the item number 2 up here. You're doing all this research, and you're figuring out what's happening. You're figuring out the here is what's happening now, the diagnosis. Then you analyze the experimentation, and finally you make a conclusion. Okay, so here's the conclusion. This does that because of this. And then once you have done that, you start all over again and go into the next level of whatever it is you are trying to figure out. That is the scientific method. Question, research, come up with a hypothesis. That's the important thing. Experiment with that hypothesis, analyze the data, and then conclude what's what. So we can do all of that with weather. This is a lot like satellite and radar. You know, radar was invented in 1935 to track aircraft. But then a few years later, somebody said, hey, why don't we just use radar just for weather? Forget about the aircraft. We're just talking about the weather. And we can track storm systems and all that. And then radar meteorology was born. Satellites were launched back in the 1950s. You know, many of them were military satellites, and they still are. And there are many other things. But then somebody said, hey, we're way up high, orbiting the Earth. Let's use that just for weather. And satellite meteorology was born. So the scientific method continues. Computer models were developed back in the 1930s and 40s for a lot of things. Well, computers, I should say, not computer models, just computers. You know, a way to artificially calculate numbers, basically. But then somebody said, hey, why don't we do this just for weather? And this goes way, way, way back to the conceptual times. So how do these weather models work? Well, here's how they work. We come up with data points that are equidistant. They are all the same distance apart, and there's a point. So here's a point right there, close to Atlanta, Georgia. There's a point. And at that point, we know what the temperature is, what the wind is, what the humidity is, what the momentum is, what the height of the different important millibar levels are, the 500 millibar level. So we know all of these things, and here's where it is right now, and we know that. And a global model means that there are points all around the world, but not just on the ground. There are vertical points too. You'll notice this, here's the ground points, but it goes vertically all the way up to the top of the atmosphere in some cases, or close to the top of the atmosphere. You never actually reach the top of the atmosphere, but you can get well up over 100,000 feet. And so there's one point here over Puerto Rico, and then there are all these other points directly above it. And each point has data on temperature, dew point, wind, pressure, density, and many other things. So now we can diagnose what the weather is like right now. Now, sometimes there are models that only deal with, like in this case, North America. That's the domain. It is not the entire world. Uh, the good thing about that is that there's less data that you have to calculate, and so you can do it faster and a little bit more high resolution. But if you're looking at the entire world, then there's just so much data, and the resolution might not be quite as good. And so that's the trade-off. Of course, if you have a domain like this, then what happens out here outside the domain? You don't have any data there. So if the weather is coming in from the west, how do you know what's coming into your domain if there's just a vacuum out there? And there are ways, of course, to solve that. But anyway, there are mesoscale domains. That's what the term is. There's a special model that is used a lot called the North American Mesoscale model. And then there are global models. And many of them are now global models. So there are four. Remember this is very important. So I hope that you're all listening, beginning right about now. Remember this. So there are four different eras in numerical prediction. At the beginning is the concept. So there was a guy named Wilhelm Bjerknes. He was a Norwegian who in 1904, so this is well over 100 years ago now, in 1904, he first wrote down the primitive equations. Primitive equation means that they are the primary equations, not that they are from cavemen. So there are momentum equations, and here you can all see they're all partial differential equations, and they deal with the east to west, or rather the west to east, the south to north, and the vertical coordination. Here we have a thermodynamic equation, which deals with the heat in the U, the V, and the W Cartesian coordinate system. U is west to east, V is south to north, and W is vertical. There are continuity equations, moisture equations. Here's the ideal gas law, which we get into some detail in the 300 course. That's pressure and volume equal density times the universal gas constant times temperature. Anyway, all of these governing equations were first written out by Bjerknes in 1904, and so only then was the idea ever even brought up. It was probably never came across anybody's mind prior to that you could actually predict the weather just by looking at numbers. That's what the numerical means there in numerical weather prediction. We're only looking at numbers. We're not looking at patterns necessarily. We're not looking at clouds or fronts. In fact, the whole concept of cold fronts and warm fronts and all that was, nobody had thought about that until now, when these Norwegians back in the early part of the 20th century came up with the concepts. So the concept was the first part of NWP. Next, we come up with the practical part. So in the late 1930s and 1940s, computers were developed. These were big computers with vacuum tubes and wires. They took up an entire room, and they were really part of World War II. So there was a lot of technological advancement in World War II for computers in particular. But then somebody said, hey, why do we use this just for weather? And then by the 1950s, we have big computers in the World Weather Building in Silver Springs, Maryland. And so it turned out that for many, well, actually decades, there was more computing power being used for weather than anything else, including national defense. So I thought that was rather interesting. That was the practical part. We could actually use numerical weather prediction, and it worked. And that was in the 1950s. Then we get to the 1990s. That is the third era of the four. And now we have really fast computers that are working 24 hours a day. And this was the 1990s. And this is what I call the reliable period. Does anybody have a question, by the way, about anything yet? Nobody has a question? All right, so the reliable period is when we really started, well, relying on computer models. I've been doing weather for over 50 years, and back in the early 70s when I started, everything was still pretty much our artisan weather forecasting. You would look at the maps, you would look at maybe radar. This was kind of before satellite was all over the place. And you would come up with a forecast. You might as well put on your chef's hat, you know. But then in the 1990s, computer model data was so prevalent and was getting better and better that people started talking about the models. I remember I was on TV, and back in the early 80s when I started television, you know, we weren't really talking computer models, but then models became a big deal long about the early 1990s. And then I would actually start talking. And the models say, people would think, the models, what is that all about? They had never heard of that before. And then the numerical weather prediction, the computer models became a big thing in the 1990s. And after a while, I was showing what the models were saying on TV. And I was like cutting edge. You know, nobody else was doing that, but I was doing that. And now everybody's doing that, of course. So those were the 1990s, and then the computers got faster and more reliable, more sophisticated. We've had up until this point the Cray XC40 supercomputer, which has been capable of making 8.4 quadrillion floating point operations per second, and that is way out there. 8.4 quadrillions. It's called 8.4 petaflops. Petaflop, the peta means quadrillion, and the flop is a floating point operation per second, is what that means. So that was a lot. But there's been an update to that, and this is now coming up on 2 years. In the fall of 2022, 2 new computers were installed in Virginia and Arizona. They have names. Let me see. The Virginia one, oh, what is it called? It has a name. The Arizona one is called, oh, I know, Dogwood. It's called Dogwood. And the one in Arizona is called Cactus. That's kind of their nickname because of the flora of those regions. Anyway, now when you link them all together, and really a supercomputer is nothing more than individual computers that are all linked up to make one big computer. So now, and these Hewlett-Packard computers, by the way, now have the capability of operating at 42 petaflops. That's 42 quadrillion operations per second. When we get into the 300 course, I actually show you how big that is. You know, how many 42 quadrillion seconds or 42 quadrillion feet. It's a lot farther than you would think. So anyway, we've gotten to the point now, and this is now 5 years ago, that basically computer models are the default. And as I mentioned earlier, the National Weather Service, they're not in the business of forecasting the weather. They manage the computers, and really they go out and they do storm surveys, and they try to keep everybody aware of nasty weather to come. They will issue warnings and watches and things like that. They keep you abreast of winter storm scenarios and all that, but they don't actually do the nuts and bolts day in, day out forecasting, even when it comes to the aviation forecasts. which is too bad, I think, because you need a human touch. At least I think you do. Whenever the models are just way off, and there are reasons that that could happen. There could be bad input data. If there's a weather balloon that goes up and it's just completely wrong about the temperatures at 300 millibars, and that gets input into the database, then that error will be expanded with time. And so after a while, there might be a bad forecast. That doesn't happen very often. Sometimes it does. So we have a thing now called the National Blend of Models, which I mention like all the time. It's the primary forecast of weather parameters. Meteorologists are only there to make changes if required. So the National Blend of Models will take all of these different inputs here. The NBM is what we call them. And it includes the Canadian Meteorological Center, that's Environment Canada, the U.S. Fleet Numerical Weather Center, that's in Monterey. Let's see, the Australian Bureau of Meteorology, plus all of these. Here's the GFS, that's the American model right there. And we have, let's see, the NAM, which is the North American mesoscale model, and there are a bunch of others. Here's the European model right here. Here's the climate prediction model right there. The models that they have. So all of that is input into the models. Now, when you're flying, we'll get to something practical now. You're flying from point A to point B, and you need to know what the weather's going to be like. In regards to ceiling, visibility, winds, and things like that, all of the parameters you need to know, and you can get that on ForeFlight, obviously, with all sorts of neat graphics that you can use. ForeFlight is what all of us at CAU use, and probably most people use that app because it's simple, it's user friendly. You can pick a location, and it'll tell you what you need to know. But you can also get MOS. Here is the MOS data. Here's the nearest TAF. All right, so you're going to get a TAF, or you're going to Gainesville, Texas, and you're going to get you come down here to the forecast. You've already got the METARs, you got the winds and all that stuff. But you can also click on MOS, which is the Model Output Statistics. So this is, and the interesting thing is usually the Model Output Statistics and the TAF are pretty similar. At least they should be. But you might want to know exactly what the difference is. So here we're going to Gainesville, and it has, here's the MOS. It says MOS right there. It'll tell you VFR. Here's the 3 p.m. forecast, VFR with winds, visibility, clouds, etc. It has all that data that you can get strictly from the never touched by human hands numerical weather prediction. Model Output Statistics, MOS is what it's called. And it'll also allow you to come up with, here's the TAF. This is from Nashville, but you can also click on the MOS. So here's the TAF once again. And if you want MOS, just click on it and bingo, there you go. You have hour by hour. Here's the 7 o'clock, here's the 8 o'clock. It'll tell you VFR gives you winds and 4,000 broken. Now it goes to 1,500 broken right here with a little bit of rain. And so that is what the MOS will tell you. And there it is. So that's pretty cool. Plus, we also have all of this. These are the winds and outside air temperatures for 3,000 feet all the way up to 51,000 feet every 3,000 feet. So that's a pretty significant information. Winds, looks like they peak right here at 33,000 feet. Here is the delta T right here. It's much cooler than normal, and the lower levels, as you can see. That's the International Standard Atmosphere, and the delta T from that. So models are a reliable resource for you. They are not always correct, but they are correct often enough so that you can consider them mostly reliable. and it's a good thing. Does anybody have any questions about computer models? And we've just sort of scratched the surface here. To get to the 300 course, we have an entire class in great detail on models. This was an introduction. Nobody has any questions? Okay. All right, so the assignment then is just to read chapter 22 of the FAA Weather Manual and read about models on weather.gov. There's a little thing to look at there. And then there's an ensemble model forecasting video that you can look at. And there you go. Next time, which means Wednesday, we'll be talking thunderstorms and hazards. So we're going to get kind of back into the really important stuff that everybody needs to know as a pilot. All right, that was it. That was kind of a little bit quicker today than usual. Barbara, do you have any comments or questions?
No, I don't for the moment.
Okay, everything is good with you?
Yep.
All right. Okay, and I guess Travis doesn't have any questions, so we're good to go. Yeah, there's one individual that still needs to take the test, and he will hopefully do that between now and midnight tomorrow night. Other than that, everybody is passing the weather portion of AER 110DE. So we're looking pretty good. One individual actually aced the test, so that was good. All right, if nobody has anything else to say, we will go ahead and call it a day and see you on Wednesday. All right?
Sounds great.
All right, bye.
Take care.